Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where I am trying to help you to achieve your dream of getting 60 out of 60 in physics. Now today we are going to discuss another chapter called properties of fluids, okay, which is not super important, but every year one questions is coming from this chapter. So if you are someone who is preparing hard for achieving that dream of 60 marks in KCET exam, then obviously you cannot skip it. But if you are someone who is somewhat struggling with the concepts, then you can skip this chapter. This is one of the chapter you can skip, but remember that for those who are preparing for out of out in your KCET exam for physics, then you cannot skip it, okay, especially those who are aiming for top 100 rank, top 500 rank, you cannot skip it, okay. For other students, those who are a little bit in the middle of the preparation and they are thinking, okay, can I skip it, this is the first PU chapter, yes, you can skip this chapter if you are not super confident. If your second PU is already not completed, then you can skip this chapter. This is a little bit difficult in compared to the time that you invest, and only one questions you are going to get it from this chapter, okay. Also, as usual, to get all the notes from our lecture, you have to join our WhatsApp channel. The link of the channel is given in the description. All the class notes, all the updates that we are doing regarding KCET 2025, all the lectures, and any update that is coming to our way for any other information related to KCET, we are going to provide in our WhatsApp channel. So this WhatsApp channel is active, and you can ask your seniors. We have there for the beginning of KCET exam, when it will be announced till the result is announced, and then your counseling process is completed, we will be there. Every update will be provided on our WhatsApp channel, so don't forget to join our WhatsApp channel. Everything at one place, right? And now let's look into the list of contents. Today we are going to start with pressure, okay, very basic thing. Then we will discuss about streamline flow, an interesting thing to know about. Then we will be discussing Bernoulli's principle, then viscosity, surface tension. Last but not the least, we are going to discuss all the PYQs from this chapter. So this will be a one shot video. Everything of this chapter will be covered in this single video, okay. So now let's start with the concept of pressure. What is pressure? Pressure is something when we keep something inside a liquid, right? When we keep something inside the liquid, it feels something which is called pressure, which is force per unit area. So if there is a liquid and if we keep an object inside the liquid, it experiences a force, okay, and force per unit area is called pressure. It's a scalar quantity, it does not have any direction. And the first law that we are going to start is Pascal's law, okay. Pascal's law states that whenever an external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all direction, okay. So what is the meaning of that? Suppose you have a ball, okay, you have a ball full of, say, water. You made some holes into the ball, okay, and then you apply some pressure on the ball. So what will happen? Liquid will come out from all the sides, right, all the holes, and according to the Pascal's law, the pressure that you apply into the ball, okay, that will transmit without changing. This pressure will transmit to all the points without any change. So that is a very, very important thing, okay. Does not matter how small or how big the hole is, the pressure will be same, okay. The transmission of pressure will be same. Now where we use this? We use this in hydraulics. What is the meaning of hydraulics? There are few things you may have heard about, okay. Hydraulic pressure, then hydraulic brakes. It is widely used in modern day cars, okay. Hydraulic brakes, okay. It is used in hydraulic press, where you use the press means not iron, okay. Press means where you print things, okay. Hydraulic press is one of the oldest form where the concept of this is used in printing material, okay. And a normal hydraulic that you may have seen is kind of like this, where you have a small pipe and a large pipe, okay. Here you apply small amount of pressure and here you get a large amount of force, okay. So you basically what you do, the pressure remains same, the pressure remains the same, but force is pressure per unit area. So if you can increase the area, okay, the force will increase, okay. The relative displacement will be less, but you can lift a heavier object by applying small amount of force, right? Hydraulic lift, this is called hydraulic lift, very widely used. So this is one of the places where this Pascal's law is used, okay. So if you apply, say if you apply a pressure P here, the same pressure you will get back here as well. So pressure will remain constant, but we know that pressure is basically force per unit area. So we have increased the area in this case, so force will increase, right? So that is the basic thing that you need to know. Okay, now let's move on to the next part. Gauge pressure. What is the meaning of gauge pressure? So this is very interesting, okay. We have a liquid, okay, we have a liquid and we want to measure the pressure. What are all the pressure that maybe we are measuring? So we have a liquid in a container. Now I want to measure the pressure here, okay. I want to measure the pressure here due to the liquid column only. If I want to measure the pressure due to the liquid only, okay, then that pressure is called gauge pressure, okay. Gauge pressure is the pressure due to liquid only or fluid only. In general, we generalize liquid as fluid because air is also considered to be a fluid, gases are also considered to be fluid. So fluid is in general. So any fluid in a place we want to measure the pressure, then that is called gauge pressure. What are different types of pressure? The total pressure, we will see that in a while, okay. And we know that the pressure inside a liquid at any point P is given by rho g h, right? Rho is the density of liquid, g is the gravitational acceleration, and h is the height, right? This is the gauge pressure. This one we know. Only the thing is the name gauge may be something new to us, okay. We have already learned about that in our 9th class, right? Now total pressure. Now we are looking into total pressure. Total pressure means if there are any other external pressure acting on this system, that also we have to account for, okay. Especially if the container is open. If the container is closed, gauge pressure is sufficient, okay. Atmospheric pressure is restricted in that case. But if it is a open pressure, thing, okay, then you have to apply the concept of total pressure, and total pressure is basically nothing but gauge pressure plus atmospheric pressure. So atmospheric pressure is there, which is already there, okay. 1 atmosphere or whatever value it is there, 1.001, whatever value is there, that atmospheric pressure you have to add, okay. Basically it is nothing but rho gh plus Pa. For most numerical cases, we will only need this knowledge. This knowledge is sufficient, okay. So this is the most important thing for KCET exam that you need to remember. Not most, but this is the only pressure that you have to remember for KCET exam, okay. Now let's move on to the streamline flow. So look into this two images, okay. How many of you have seen this kind of motion? So here you can see the water is not clearly visible. It has a lot of bubbles and the water looks like hazy. But if you see here, the water looks clear. But what is the difference between these two things? So here the tap is opened fully, okay. So the water is moving with a very high speed, and that's why all the turbulence, this is called turbulence, okay. In between the motion of the liquid, in between is called turbulence. So all the liquid flow is flowing is turbulent motion, okay. So turbulent motion means the flow is hazy, Okay, this kind of white is milkish thing is coming. But when you reduce the water pressure, reduce the flow, okay, you will see that water is flowing slowly, but it is appearing to flow with the constant motion. There are very few very good animations available on YouTube. You can check that streamline motion, where it is appearing that the liquid is not at all moving. Okay, even though the liquid is flowing, if the motion is streamlined, you will not be able to ascertain without touching it that whether the liquid is in motion or not. Okay, generally streamline motion occurs at a very low speed. Okay, so streamline motion is when the flow of fluid is said to be steady if at any given point the velocity of each passing fluid particle remains constant. So velocity of each passing particle remains constant, then we say that the flow is steady. So each particle is constant, each of the particle has a constant velocity, so they are not accelerating, right? So that is called a steady flow. Okay, the path taken by a fluid particle under a steady flow is called a streamline. Streamline is the path followed by it. Okay, so streamline motion means when the liquid is moving, all the particles in the fluid is moving with a constant speed, and then the path followed by it is called streamline. In most of our discussion will be restricted to streamline motion only. The formulas, the equations that we will study will be mostly for streamline motion. For turbulent motion, the equation becomes difficult, becomes little bit more complicated, but we are not going to discuss that here. Those who will study aerodynamics etc. in future in engineering courses, they will study all those things in your engineering course. Right now we are not interested in that. So it is defined as the curve whose tangent at any point is the direction of the fluid of the velocity of the fluid at that point. So at any point if you draw a tangent, then the tangent should provide the direction of velocity. Okay, so if you say this is a streamline, this is a streamline, then at any point if you draw a tangent, then you will get the direction of velocity of the liquid fluid particle at that point. So that is the basic definition of streamline motion. Okay, now, so Bernoulli's principle, another important principle. So as you can see, this chapter is very theoretical chapter. Many theories are there. Another is Bernoulli's principle. Okay, Bernoulli's principle is that when liquid is flowing through, suppose we have two surface areas. First we are learning about flow rate. Okay, we have two surface, one is this and one is this, a streamline motion, a liquid flowing with a streamline motion through this. Okay, that is a constant motion. Now what will happen? Steady flow, the flow is steady. Then the speed of fluid at this edge is say V1. Okay, and at this end it is V2. Then what is the relationship between A1 V1 and A2 V2? So we call this as flow rate. Okay, flow rate, say capital R, it will be constant, and that is nothing but A area times velocity, it is constant. Okay, so what is the meaning of that? In this case we can write A1 V1 equals to A2 V2. Okay, this is the flow rate. R equals to AV is called flow rate, and A1 V1 equals to A2 V2 equals to A3 V3. Suppose this now goes on and it becomes smaller, it becomes bigger, then every case area times the velocity will be constant. Okay, even in this case, suppose in this case, as you can see, the area is changing, so velocity will also change. Okay, area times velocity will remain constant at any point in the fluid motion. Okay, so this is called equation of continuity. This equation is called equation of continuity, and the term R equals to A times V is called flow rate. Okay, this is constant. Okay, now let's look into the Bernoulli's principle. We have a tube like this. Okay, the liquid is flowing through this tube. Okay, height of this point is h1, the area is a1. okay, and height of this is h2, area is a2, okay. Don't go into the derivation, just formula is sufficient. Then we can write that P plus half rho v square. Rho is the density of the fluid, rho is the density of the fluid, v is the velocity of the fluid, plus rho gh, h is the height, okay. So P plus half rho v square plus rho gh is constant. This is Bernoulli's principle, okay. So at this point, suppose velocity is v1, here pressure is p1, then we can write p1 plus half rho v1 square plus rho gh1 equals to p2 plus half rho v2 square plus rho gh2, okay. So this is the basic principle of Bernoulli's principle. This is a complicated mathematical equation. Bernoulli's principle has also a simpler meaning. What is the meaning of that? If the liquid is flowing with a higher velocity, okay, so if you consider this term and this term are same, okay. So suppose you have a pipe which is horizontal. Suppose, let's take a horizontal pipe, cross section will be different. Suppose you are considering a horizontal pipe like this, okay, something like this, suppose, okay. Both of them diameters are at the same height from the ground. So this is also h, this is also h. This has a velocity say v1, this has a velocity say v2, okay. Pressure is here is p1, pressure is here is p2. Then from Bernoulli's principle you can say that p1 plus, from this formula, p1 plus half rho v1 square equals to p2 plus half rho v2 square, right. This is the simplest formula when the horizontal height is same, okay. Only velocity is different and pressure are different. So basically if velocity is more, okay, the pressure has to be less, okay. Suppose v1 is more than v2, okay, v1 is more than v2, then the corresponding pressure will be less compared to this. Why? Because the total term should be constant, okay. So if suppose this is 100, this is 20, so total value is 120, okay. Now suppose this is 80, then what will be the pressure? Pressure will be 40 now, because sum should be constant, that is 120, right. So 100 plus 20, here if the pressure is reduced in the velocity is reduced in this case, that velocity total term is now 80, then that value has to be, pressure has to be 40. So higher the velocity, less is the pressure, okay. Higher the velocity, less is the pressure. That is the fundamental interpretation of Bernoulli's principle, and most of our some important objects in our day-to-day life are based on this principle. For example, the motion of a plane, okay, we fly, okay, we fly from say Bangalore to Delhi, okay, or Bangalore to Chennai, we are using a flight. So that flight actually operates based on the Bernoulli's principle, okay. There are some other principles added to it, but the basic funda is this Bernoulli's principle. As the velocity is more, okay, pressure will be less. Less pressure means air will try to push from higher pressure to lower pressure. That's how the plane gets the lift, okay. That's how the plane gets the lift. The design of the plane is such that it can move such a way that it gets a lift and it can fly in the sky. Same thing is applicable for birds as well, okay. Also sometimes we open book pages, two pages are attached to each other, we apply air from our mouth to separate the pages, okay. So what happens is that when the air flows, okay, both side of the paper, the pressure decreases. So inside pressure is more than the outside pressure, so the paper easily folds, opens. Okay, it does not, because the air goes inside. Air does not go inside the fold. Okay, air only passes through the side of the paper. So there are many good experimental practice based on Bernoulli's principle. If possible, I will show you sometime some of them in future. Right now, let's move on to the next part, speed of efflux, or in case of Bernoulli's principle. What is the meaning of speed of efflux? We have a closed container. Okay, container is closed and some fluid is coming out of this hole. Okay, there is a hole and through which some fluid is coming out, and we are trying to measure the speed of this fluid that is coming out. Okay, so the speed of the fluid that is coming out of the this hole is given by 2gh, P outside minus P atmosphere divided by rho. Okay, so here this is P atmosphere, this is P2 or PO. Okay, here you can say this is PO, whatever pressure is here. Okay, so this is the expression for speed of efflux when the container is closed. Now when the container is open, suppose we have a open container. Okay, most of our containers are open. For example, you are drinking water from a glass, so that is an open container, right? And in this case you have a water bottle which is fitted with a cap, and then somehow this got leaked, there is a hole into that. Then the speed will be different than there is no cap. Okay, you can try using your old cold drink bottle. Okay, you can take a small 1 liter cold drink bottle and first fill it with the water. Okay, and then make a small hole into this, and then do the experiment with the cap on top. And then once you move the cap, what happens? Okay, in both cases the speed of efflux will be different, right? So this is the case where the cap is on. Now if the container is open, then what happens? This is PA, atmospheric pressure, this will also be PA, right? So on top of the water, this pressure will also be PA, and the pressure here from the outside will also be PA. Okay, so this both term PO and PA both will be equal. So for open containers, you have to remember that for open containers, PA equals to PO, therefore V1 equals to square root of 2gh. Okay, this is for open containers, only square root of 2gh will be there. Okay, simple. Now let's look into a problem that came in last to last year, that is 2023. So what is the question? A closed water tank has a cross sectional area A. Okay, it has a small hole at the depth h from the surface of the water. The radius of the hole is r. Okay, so that r is very smaller than a by square root of a by pi. Okay, if P naught is the pressure inside the tank, P naught is the pressure inside the tank. Okay, and PA is the atmospheric pressure, the rate of flow of the water coming out of the hole is, okay, rho is the density of water. Here rho is the density of water. Okay, now how to answer this question? So here, as you can see, the tank is closed. Tank is closed means speed of efflux, we know that will be equals to 2gh, okay, plus 2 PO minus PA divided by rho, right? So this is the formula for speed. Now rate, flow rate. What is flow rate? I already told you flow rate is area times velocity. Now what is the area here? This is a circle, so area will be pi r square, right? This is the area, right? This is the required area, so pi r square times this value, entire thing, right? So you can see only one option is correct, that is option A. So if you only remember the speed of efflux formula, okay, then only it is sufficient to answer this question. Okay, now that is why it comes, this I said that this chapter is slightly difficult. If you want to derive this thing, it will take a lot of time. The derivation for this is at least 5 to 10 minutes work, okay, deriving this formula. But if you remember the speed of efflux formula, then it is very easy to solve this question. Now let's look into the next concept, which is viscosity. So the law that we are going to learn from this is Stokes' law. So first, just give you a basic idea about viscosity. Viscosity is nothing but when liquid is flowing in a okay, they also give some friction. Like friction is there when we are walking or moving on a surface, right? Similar to that, when liquid is moving, they also collide with each other and there is a friction. The liquid friction or fluid friction is basically termed as viscosity, and it also has a coefficient of viscosity like coefficient of friction. If you remember, coefficient of friction was given by the symbol mu, right? Coefficient of viscosity is given by the symbol eta. Okay, it's like a small n, then you increase one of the side and then you just make it a little curve. Okay, so to make it look good. Okay, otherwise in computer letters it looks like this. Okay, it's like a small n with one arm extended. Okay, I like to write it like this so that it looks good. Okay, so now what is Stokes' law? Stokes' law says that when a body falls through a fluid, it drags the layer of the fluid in contact with it. Okay, the drag force is given by F is equal to 6 pi eta RV. Okay, so suppose there is a layer of fluid, layer of air present. Okay, this is the layer of air. Now if you drop a ball, okay, this ball will drag the layer which is close to it. So when the ball is here, it will basically drag this layer with it. Okay, you may have seen some animation where the hero shoots a bullet and bullets was passing through the air. Okay, so the air is moving along the bullet, right? So there are some nice animation, nice motion. Okay, so that is basically because of the Stokes' law. Okay, so the bullet will carry the air through it and it will experience a drag force. Now it is not normally possible to watch in our regular eyes, but if you shoot it in using a slow motion cam, then you can maybe you can see that. Okay, and that drag force is given by 6 pi eta RV. So more dense the fluid is, so if you are shooting in the water, the drag force will be very high because water has a very high viscosity. But if you are shooting in air, okay, it has a lesser velocity, so it will have a less amount of drag. Okay, more drag means it will try to pull it back. Okay, try to stop it. That is the main concept, right? Same thing for friction. So when you are trying to move, friction is trying to pull you back. Same thing is here for liquid or fluid, okay, or gas. So there is a drag force which is trying to stop it. Now this formula is very important. There was a question in electromagnetism came last year based on this Stokes' law concept. Okay, so don't ignore that formula. You have to remember the basic structure of the formula. Now let's look into the surface tension. Have you seen this kind of thing? Okay, there is a small bug who is floating in the water, but he is not swimming. He is just staying there on top of the water surface. How it is possible? Okay, so as if this water body is acting like a rubber band or balloon. Okay, the skin of a balloon, you see that, right? So you can think this is the skin of the balloon and the bug is sitting just like that. So what is happening here? There is a property of fluid which is called surface tension. Especially it is observable in case of liquid. Okay, and this surface tension is actually, the liquid surface behaves like a stretched balloon surface. Okay, and that is why, but it is not, if you drop this pen, suppose if I drop this pen, it will not float, it will sink because it has a lot of weight. Okay, for lighter object like this bug, it can float on using this surface tension. There are a slightly more biological mechanism as well. Okay, they have their skin has lot of hairs, so that increases the surface tension. That is also one of the reason, but this is very cute to see. right? Next time when you visit a lake or some water body, try to spot them. Okay, now the formula for surface tension is given by force, applied force divided by 2L. Okay, L is the length. This is one of the formula where you try to drag soap bubble. If you try to drag a soap bubble like this, if this is L and the force you applied is F, then surface tension is given by S equals to F by 2L. Okay, in fact, if you have ever played the bubble game, okay, where you soak your bubble spray inside some liquid and then you blow some air, it forms bubbles. Okay, bubble guns. So you have some liquid inside your gun and you press the trigger, it will throw off some bubbles. So these are basically these are possible because of the property of fluid called surface tension, and because of the surface tension it can have this kind of shapes. Okay, so these are very funny things that you can in your childhood memories. Those are very fond memories for me. So we used to play in a fair, village fair. When we used to go, we used to buy this liquid water and this thing, and then we put some air, blow some air, it produces bubbles into it. Right, now one more important thing. Okay, so now one more important thing is capillary rise. What is capillary rise? So if you take a tube, okay, if you take a tube and if you put it inside a fluid, okay, the fluid will rise into the tube. Okay, so you can try it using your empty pen refill. If your refill is empty, okay, you can take this out. Do not try to using a gel pen refill, but if it is a normal pen refill, dot pen, if you have any dot pen, or you can try using a straw. Okay, if you went to the shop and drink one coconut water, you can try to bring that straw home and you can try this experiment. Okay, if you put this inside the water, water will rise into that small pipe. Okay, so this is called capillary rise. The height of this liquid is more than the height of the liquid, so this is called capillary rise. Okay, now this is happening obviously due to surface tension, and the expression for capillary rise, the height is given by 2s cos theta divided by rho g r. What are all these things? S is obviously the surface tension, cos theta is the angle of this meniscus. Okay, so this is the angle of the meniscus, this angle is theta, so then it is called cos theta. So 2s cos theta. Okay, r is the radius of the pipe. Okay, so you can see that the height of this capillary rise is inversely proportional to the radius. So thinner the pipe, higher it will rise. Okay, if you just simply put on a bigger cylinder, the rise of the water will not be much. Okay, but if you use thinner pipe, okay, more thinner the pipe, higher will be the rise. So if you use a thin pipe, the rise will be more, okay, compared to the basic thing. Now remember that there was a formula due to which, okay, if you cut this, suppose there is this is the capillary tube, okay, and if you have you have some water, some liquid flowed into this. Now what will happen if you cut this pipe at here? There is a very common question come in your some of the questions. Okay, it is available in NEET. Sometimes it might come in your JEE, might be because it is a common question, might be it is coming to your KCET exam as well. Remember that if you cut that capillary tube here, the water will not go up and it will not create an infinite fountain. It is not possible. Okay, the infinite fountain will not be created. Instead, what will happen, water will rise to the maximum height. Suppose you have cut this and you have created a pipe which is suppose the smaller than this height h. If the height it is smaller than this height h, the liquid will rise to the maximum possible height and then it will stop. it will not be overflowing. Okay, this is a very simple law that you have to remember. Water will not be overflowing, it will stop at the maximum position. Okay, now this is just a side knowledge that it may be very handy for you. Let's look into the PYQs now. First PYQ is, the capillary tubes P and Q are dipped vertically in water. The height of the water leveling capillary tube is, tube P is 2/3 of the height of capillary tube Q. Okay, so height of the capillary tube P is 2/3 of the capillary tube Q. Okay, the ratio of their diameter is, so what is the question? So height of capillary tube P is 2/3 of the height of the capillary tube Q. Okay, so you have to find the ratio of their diameters. Now what we know? We know that capillary rise is inversely proportional to the radius. Okay, so height in the capillary, if you remember the last part that we discussed, height of the capillary rise is inversely proportional to the radius. So, or we can say that it is inversely proportional to the diameter as well. Why? Because diameter is 2r. So this is just a constant. So if something is inversely proportional to radius, the same thing will be inversely proportional to diameter as well. Now, so we can write this P divided by HQ equals to DQ divided by DP. Inversely proportional, right? So HP and DP will be in the corner like this, right? Inversely proportional means it will be opposite side. Now, what is HP? HP is 2/3 HQ. So 2/3 HQ by HQ equals to DQ by DP. Right, so HQ cancels, so DQ by DP is 2/3 or DP by DQ equals to 3/2. So why I have done DP by DQ? How do I know? Because in the question first is P, next is Q. So in my answer will be, first will be DP, next will be Q. Okay, so it will be 3:2. Okay, clear? The answer will be 3:2. Next question from 2020. Iceberg floats in water with the part of it submerged. Okay, what is the fraction of volume of the iceberg submerged if the density of the ice is rho I equals to 0.917 gram per centimeter cube? Okay, now this question is based on Archimedes principle, which is based on your class 9 syllabus. So in Archimedes principle it says that suppose the volume of an object is V. Okay, density is rho. Then what is the mass of this object? Mass of this object is very simple, V times rho. This is simple, right? This is from the definition of density. Mass per unit volume is density. So mass is basically volume times density, right? Now if you put it inside a fluid, okay, and if the object displaces, say, a volume of X, if this object displaces a volume of X and the density of the liquid say rho L. Okay, then what is the mass of the displaced liquid? Mass of the displaced liquid will be equals to mass of the displaced liquid will be X times rho L, right? This is the volume of the displaced volume of the submerged part. So whatever part I have been submerged into the liquid, the same amount of liquid will be displaced and the mass will be given by rho XL. Now Archimedes principle says that the weight of these two will be equal. So mg will be equals to small mg will be equals to capital Mg. So because g is constant, we can cancel them. So V rho equals to X rho L. Okay, now in this case volume of the iceberg is V and its density is given by 0.917 0.917, 0.917, and x we don't know. What is the density of water? Normally density of water is 1 gram per cc. Okay, assuming it is in 4 degrees Celsius, so it will be 1 gram per cc. So x will be 0.917 times V. So 9.917 fraction of initial volume will be submerged. Okay, so the volume, the density is 0.917. So 0.917 of the iceberg will be submerged into the fluid. You can answer this question even if you don't know the question. Okay, if you read this question, only one value is matching. So even if you guess it, might be it will be correct. Okay, now let's move on to the next question. An aluminium sphere is dipped into a water. Which of the following is true? Now this question does not have anything to do with this aluminium sphere, unfortunately. Okay, let's check the options. Buoyancy in water at 0 degrees Celsius will be same as that in the water at 4 degrees Celsius. Buoyancy will be less in the water at 0 degrees Celsius than that in water at 4 degrees Celsius. Buoyancy may be more or less. Okay, buoyancy will be more in water at 0 degrees Celsius than that of water at 4 degrees Celsius. This is obviously does not make any sense, so I have not even tried to read it. Okay, so we know that buoyancy is maximum at 4 degrees Celsius, and slowly it decreases on the both side of the graph, right? So that is called anomalous expansion of water, if you have studied that in your previous class. So buoyancy will be less in water at 4 degrees Celsius than that in the water at 4 degrees Celsius, right? So buoyancy will be less at 0 degrees Celsius, higher at 4 degrees Celsius, right? So this is the correct answer. This is the correct option. Okay. Now, next question. A cylindrical container containing water has a small hole at height of capital H is equal to 8 centimeter. So, at a height of capital H, so this is 8 centimeter. Okay, at a height of 8 centimeter, there is a small hole. Okay, from the bottom, and depth 2 centimeter from the top. So, from the top it is 2 centimeter. Okay, so the same hole from top it is 2 centimeter, from bottom it is 8 centimeter. Okay, and it is open. Obviously, as you can see, the container is open. The maximum horizontal distance traveled by the water before it hits the ground. So maximum horizontal water distance it travels before it hits the ground. Okay, so what you have to do, suppose this is the container, okay, this is the hole, okay, it will hit the ground after some time. You have to find this horizontal distance. Now looking into the image, can you find anything similar with something that you have already studied? If you have, then please mention that in the comment below. What is this is similar with? Okay, also if you are enjoying this session so far, don't forget to subscribe to our channel. Okay, now so this is basically, you can compare this with the thing that we have already studied, is called projectile, right? So we don't need to any new formulas or new equations. Only thing you have to apply the basic concepts of projectile. First of all, what we know that the speed with which it is coming out is speed of efflux. Since it is an open container without any cover, we can write the speed of efflux will be equals to square root of 2g h. H is here is from the top of the container. Okay, so H here is the top of the container, so it will be square root of 2 times G times let me keep it like this as only. Okay, let me keep it like this only, don't mix it. So V is 2G, square root of 2GH, that we know. Now how can we find this range? Okay, now as you know that this is a horizontal speed, so horizontal speed will not mix with the vertical speed. Vertical speed will be different because only gravitational acceleration is acting in the vertical direction, so you can consider this to be a projectile. Okay, you can consider this to be a projectile as if it is projected like this, and if we can find this time required from the drop to reach from here to here, if we can find that time, then we can find the horizontal range as well, the same concept that we used in case of projectile, right? So how much time it will take? What is this height? This height is capital H. This height is capital H, right? So, and what is the acceleration? Acceleration is g. If time taken is t to reach from here to here, then we know that s equals to ut plus half at square. Here u is 0 in this direction. Initially there is no velocity, downward direction. So from here we can calculate the time t. T is 2h by g whole root. So this is the time for this drop to reach from here to here if there is no horizontal motion. Now horizontally also it is moving. So what is the range? So range is nothing but horizontal speed times total time taken, time of flight, right? So this is the range. So square root of 2gh times square root of 2 capital H by g. Now both g's are under root. Okay, one is in the numerator, one is in the denominator, so we can cancel them. Both g's are under root and both of them are one is opposite side of the division, so we can cancel them, right? So our equation becomes square root of 4h 2h, not 2h, one small h, one capital H. Okay, so square root of 4 becomes 2, right? Now what is small h? Small h is 2 centimeter and capital H is 8 centimeter. So if you use it at the last moment, see, there is nothing else is involved, so you can use it in centimeter. Otherwise you have to convert it into meters, again convert it back to in centimeter. But if you have kept the values as it is, then lastly you can simply use the centimeter values. Okay, so 2 times, what is the 2 into 8? 2 into 8 is 16. 16 square root is under root of 16 is 4. So 8 centimeter. So the water will travel 8 centimeter before it hits the ground. Interesting question, slightly tricky, slightly long, but if you know the process of it, if you know the concept of this question, then you can answer it. Okay, but it is a little lengthy question. Okay, now let's look into the question number 5. The pressure at the bottom of a liquid tank is not proportional to the. So the pressure of the bottom of a liquid tank is basically rho g h, and if you are considering the total pressure, then you have to consider the atmospheric pressure as well. We don't know what they are asking about. Let's see. Acceleration due to gravity, it is proportional to, yes, it is proportional to acceleration of gravity. Density of the liquid, yes, it is proportional to density of the liquid. Height of the liquid, yes, it is proportional to height of the liquid as well. Area of the liquid surface, is there any area of the liquid surface present in this equation? No. So definitely this is not what it is dependent on. Okay, the question is liquid tank is not proportional. Okay, so be careful about this term, not. Okay, not means you have to find the wrong thing. Okay, so A, B, C are correct, only wrong is D, so that will be your answer, right? Now next question, hydraulic lift works on the basis of, we already learned that in our first part, hydraulic lift works on the principle of Pascal's law. Okay, it is not Stokes' law, not Bernoulli's law, not Torricelli's law, only Pascal's law. Next is, an ideal fluid flows through a pipe of circular cross section with the diameters 5 cm and 10 cm as shown. The ratio of the velocity of the fluid at A and B is. So suppose velocity here is VA, velocity here is VB. Now what is the equation of continuity? According to equation of continuity, area A times VA should be equals to area B times VB. Simple, very simple. This is a very simple problem. What is area A? Area A is pi r square. Here r is diameter A by 2 whole square, right? Because diameters are given. But don't be afraid. Okay, now it will be pi diameter b by 2 whole square times VB. Okay, pi cancels. Okay, now you can write VA by VB equals to diameter DA by 2 whole square divided by diameter, it will be diameter DB by 2 whole square divided by diameter DA by 2 whole square. Cross multiply, this will come down, this will stay at up. Right, now both of them has a by 2, so the by 2 will be cancelled, so it will be simply DB whole square divided by DA whole square. Right, now what is DB? DB is given here as diameter of the B is 10 because it is more, right? So it will be 10 square. And what is DA? DA is 5, so 5 square. Okay, so it will be 100 divided by 25, that is 4. Okay, so it will be 4:1. Okay, 4:1 is the answer. So speed of fluid at A and B. So A and B order is very important. Now you should remember that A is smaller, B is bigger. So speed at A will be bigger, speed at B will be smaller. So that's how our answer matches with this thing, right? Now, so we have reached the end of today's lecture. If you enjoyed this session, don't forget to subscribe to our channel, and we have a dedicated playlist for KCET 60 out of 60 in physics, where all the videos that we are doing in our channel is getting uploaded here. Okay, also I have done one video on how to master physics, that is also available in our channel. You can check that, how to master physics in 3 months. If you want to dedicate 3 months of your time to master physics, then definitely it will going to help you. And also remember that if you are watching this video for the first time, don't forget to subscribe to our channel and share it with your friends. Also join our WhatsApp group, so that every weekend we are doing KCET Premier League, KPL. Already 11 games are over, 12th game will be this Sunday. So you have to join our channel so that you don't miss out on any single update. Also KPL question paper you can download from there, and share it with your friends so that more and more people can join our channel and get benefited from this. So I'll be back with a new chapter tomorrow. Till then, bye.